All right, howdy guys. There are a couple of things that we want to address. The first question is a question of the lab and some simple. And I want to just talk about the numbers that one student got that agreed pretty well with the numbers that I got, so that when you guys go to do your calculations, you can know if you're on the right track or not. So Joseph sent me his data, and he was perplexed about something. And as we worked it through, we found out there were actually a couple of issues. When he calculated the moment of inertia, he got a value in the neighborhood of 1,450 gram inches squared, which is not that far off from what I got by doing a different method, a calculus-based method. And when you actually convert that into kilogram meters squared, which you'll need to do, then you get something in the neighborhood of 9 kilogram meters squared. Now your number is going to be different from this, but they're going to be somewhere in this ballpark, right? So that's the first thing. I said 9. I forgot my exponent. Try that again. 9 times 10 to the minus 4 kilogram meters squared. That's a huge difference. It is tiny. And that's not surprising, because it's just a flimsy little piece of aluminum. When we actually did the experiment, and he did the calculations from that experiment, he got something around the neighborhood of 7 times 10 to the minus 3rd kilogram meters squared. Don't be fooled. This is 70 times 10 to the minus 4th compared to 9 times 10 to the minus 4th. So that's a factor of somewhere around 7 or 8 different. Those are really, really different numbers. And so the question is, what does that mean for us? Well, it means for us that either our calculation failed, or our experiment failed, or both. So we now have to go through and think about what factors might have been problematic in the experiment, or go back and look at the calculation and say, do we screw up on the calculations? And as far as getting the calculations right, we want to compare the results that we got to other people. That's why I'm sharing these numbers with you, so you can see whether or not you're in the right ballpark. Yeah.
So calculating it, it's different from the experiment. The experiment one is when you took a video of it.
Mm-hmm.
Okay.
Yep. And the calculating is when we subdivided it into smaller grids and added up in marked square in the spreadsheet. Yeah.
How do you, now that I have the string video, how do you use it to find the coordinates?
For center of mass. Yeah.
What do you call it at the corner in the string?
So you end up with these two different videos, right?
I just have one video.
In one video.
I have one video where it gets turned.
With both of them. Okay, that's fine.
That's fine.
What you probably best if you can split that into two. Just make it
You can just
slightly
take a
easier.
screenshot with both different ones.
Something. Well, I'll show you what I did, and you can figure out what it is that you want to get.
So I'm thoroughly confused.
And so what I did was I went and just put my origin right there, and I rotated my axes so that this is the x-axis and that's the y-axis, like so.
Yeah.
And you know the length of your thing, so that enables you to put a scale on there as well.
Mm-hmm.
What you have now is a string that's hanging down like this, like so. And you know that the center of mass lives on that string. So what I did was I just marked some points, up, like that, and looked at their x and y values, right?
Mm-hmm.
Then you have a different video that shows this guy right here, and again, the center of mass lives on the string. And again, you place your origin at the same spot, the same physical spot, and the axes in the same physical orientation, like that, on the same scale. And now you can take a look at points on the string here, and if you have your axes and origin set, one of these points is going to be the closest to one of those points, and that's going to be the point of intersection, or the intersection.
Why did you take two different videos?
Because I wanted to be able to put the origin on each one. If I do it all in one continuous video, then I can't move my origin.
Yeah, but what's
within
the
that
point
video.
of the string and finding the center?
I just explained all that in
Yeah.
words. The center of mass lives on that string because that's where gravity is pulling down through. And the center of gravity, force of gravity always pulls down through the center of mass. If I take any object and I let it freely hang, then it will line itself up so that the center of mass is directly underneath the point that it's hanging from. So we took our piece of metal and we attached and we let it hang freely together with a string to mark where it was hanging from. And when it did, its center of mass lined up with that string.
That makes sense.
Yeah. Any other questions about the lab? Okay, good. Let's see here.
Why do you fix the chemistry table? You look like you have a headache.
I don't have a headache. I'm a little tired and feel time crunched. So we're going to talk. We're going to just do some more rotation. And I think probably the place to start is with any homework questions that you might have about the homework that you had over the weekend. No homework questions. Fantastic. All right then, we're going to take a look at number 20, I believe it is. Give the book.
What?
I just need to look at the problem.
Oh, it's on my iPad, so.
Give a matching case of experiments.
I don't know what.
Okay, so we're going to take a look here at page 249, number 20. And what we're told is that a coffee shop, actually it's an auto repair shop, excuse me, it has a sign that weighs 245 newtons and suspended on a pole like this. And I'm just going to represent the sign with its weight right there. Now, if this were the whole story, then that sign would rip the pole right out of the wall. But it supports the sign with a cable right here, and this cable makes a 35-degree angle with the sign. And it asks us now to find the tension in the cable and as well the force on the pivot at the wall. And there's a couple of things I like about this problem. The reason that I chose it was because, first of all, it introduced something to us, something that we haven't dealt with a whole lot, and that is forces at angles that we have to worry about, of course. And the second is it introduces us to the idea of forces on a pivot at a wall. And so I want to take and examine that just a little bit. This pivot at the wall is actually going to experience a fairly significant force, and there's two reasons for that. The first is that the cable, as it pulls in this direction, is going to have a tendency to pull the pole this way and to force it to go through the wall. So that the first job of the pivot is going to be to support that pole and keep it from punching through the wall. It's going to have to exert a normal force back in this direction. So we're going to call that Fx, the force of the pivot in the x direction. And the second thing that this pivot is going to have to do is it's going to have to keep the pole from rotating downwards, because this pole is going to have a tendency to go like this, just like that. And so to keep it from doing that, the pivot is also going to have to support it in this direction, like so.
I'm sorry. I was sent in here to look for someone's vitamin water. This is it. Thank you. I'm sorry.
Yeah, no problem. With the sign, I was tempted to say, en français, s'il vous plaît. Okay, and so there we go. So let's see, how are we going to start?
Putting origin point.
Bzz.
Free body generator.
Thank you. We're going to need a free body diagram with all the forces marked here. So we're going to have a 245 Newton force here. And in addition to marking the force, we also need to mark its distance from the left side here. And according to the problem, that distance is 1.70 meters. And we are going to have, of course, a tension in the cable at a 35-degree angle. And again, according to the problem, that is at a distance of 1.35 meters. And then we have our Fx and our Fy. And both the Fx and the Fy are being exerted right at the wall, so they are at a zero distance from the left end. Are there any forces that I have left out? On what? On the cable. And the cable probably has negligible weight to it. But the pole not so, right? And so there's probably a weight to our pole. Does the problem give us any guidance about that?
Yes, it has 155 Newton.
Aha! 155 newtons worth of pole. And where does that pole? Uh-huh. And what distance from the left end?
Halfway across, so half of 1.7.
Yeah, what is half of 1.7? 8.5?
No, there. Yes.
0.85. There we go.
If we made the origin point where the cable comes in, would that mean you wouldn't have to lose that?
If you made the origin point where the cable comes in, that means that the torque from this would disappear. But in exchange, you get torque from these components here.
Yeah, but wouldn't that be easier since you don't have to deal with all the cost of stuff? entangled?
That's a great question. So let's actually work this and see how that works out. Okay? So now we have our free body diagram. Once we have completed our free body diagram, we are going to now say sum of forces or sum of torques about a point. And here, because I have three different forces, this one needs labeling, tension T. Because I have three different unknown forces, it seems to me that if I did sum of forces, it would be hard for me, excuse me, it would be hard for me to come up with an equation in one variable. But if I do sum of torques with a cleverly chosen point of analysis, then I can maybe make some of these forces disappear.
So I'll have to pivot point.
Yeah, that's right. So let's take that pivot point, and we're going to call it point A, and we're going to do sum of torques about point A. And we're going to walk from left to right and include all of them. Now the Fy is at a distance of 0, so it disappears from my equation for torque. Same thing for the Fx. The 155 newtons is at a distance of 0.5, and it is clockwise or counterclockwise around A?
Clockwise.
Clockwise, so negative. The tension, this is the new thing here. The tension here is at an angle of 35 degrees from the beam. Therefore, when I include that angle, I have the tension times its distance, which is 1.35 meters, and here it is, times the sine of the 35-degree angle. That wasn't so hard. And then finally, we go down and we have a clockwise torque. I need more room. A clockwise torque of 245 newtons times 1.70 meters times the sine of 90 degrees, which is invisible. And all of that adds up now to 0 in order for this whole thing to be in balance. Well, I look at my equation and I say, hey, that's pretty good. I've got one variable in my one equation, and I can solve for t.
So Patrick, Joe?
I mean, should have already gone.
And why is it 35?
Because torque in general is force times distance times the sine of the angle between the force and the distance. And that's giving us force times the perpendicular component.
417 or something. 1.7 times.
I say 7.
416.5.
I got 7.
What are you doing? 245 times 1.7.
Yeah, I gotta say 7.
TA
Yeah.
40.
Well, let's see here. We're getting some discrepant results. Let's compute. We should have 155 times 0.85 plus 245 times 1.70. And that gives us the negative components there. That gives us negative 548 Newton meters plus T times, and according to the calculator, it's 1.35 times the sine of 35, which is 0.774. So that when I actually solve,
Oh wait, you forgot the other part. 245.
no, I included all that here. Oh, silly calculator. Try again. 548 divided by 708. So that we get 708 newtons as the force T. Okay. And now we're going to do just a rough check to make sure. Well, actually, we can do a direct check by plugging back in. When you plug back in the T, you should get something close to 0 in your calculator. Verify that that is so. Okay, and when you actually punch it in, what do you get? Christian, what did you get?
When we plug T back in,
Uh-huh.
I got 0.24.
0.24, which is basically 0. Right. For the amount that we're dealing with. Okay, good. Now that I have the tension, I have some options. Again, I can do forces in the x and forces in the y. And that's not a bad approach here. But it occurs to me that if I choose another point of rotation, I might get lucky again and simply end up with one equation and one variable. So I'm actually going to do that. And I'm going to take the one that's been suggested. I'm going to call this guy point B right here. And I'm going to do sum of torques around point B to see what happens.
There's still y, that's still some x.
Yeah, let's see what happens to those. So if I do the sum of torques around point B, again, I'm going to go left to right here and add up all of the torques that are occurring around point B. Let's start with force Fy. Force Fy is at what distance from B?
135.
Yeah, 1.35.
What did
And it is at a 90-degree angle, so it's times the sine of 90, which is invisible. And it is a clockwise rotation around point B, so we give that a negative sign, just like that.
wait, clockwise? Yeah.
Yep. Now, fx is really different, and here we have to visualize this properly. Fx is pushing straight into point B. Can everybody see that? Which means that its perpendicular distance to B is actually 0. Now, if you have a hard time visualizing this, take a look here. I'm going to stick out my hand, and Alexis, I'd like for you to push directly in towards my shoulder. As she does, what tendency is there to rotate around the shoulder? None whatsoever, right? Because she's pushing straight in at the shoulder, and if I take the perpendicular distance to that push, there is 0 tendency to rotate. Move that just a little bit, and all of a sudden we get a tendency to rotate, see? And the further out we get, the greater the tendency to rotate around. So fx, as it turns out, drops out of our equation. And that was nice. Okay, continuing on, we have the weight, and the weight is 155 newtons. what is the distance between the weight and point B?
Subtract 135.
What?
Subtract 0.85 from 1.3.
And you get 0.5 meters, that's right.
What? Oh.
And is it clockwise or counterclockwise? It is going to be counterclockwise, it's going this way, towards smaller numbers on the clock.
Which means it's positive.
So this is positive. And then we get to the tension. The tension is being applied directly at point B, so it is at a distance of 0. It drops out of my equation. And then finally we get to the 245 newtons on the left end, and that is at what distance from point B?
0.35.
0.35. And is it a clockwise or counterclockwise rotation?
It is a
Yep, so we really need to subtract it here. And all of this is equal to 0. And this allows me to solve for Fy. Go. Solve for Fy.
What time do you think we'll be able
As soon as I can get to it.
I should know if it's maybe like later.
No, I'm going to stay and get all that up. When I solve for Fy, I encounter a bit of a surprise. The Fy that I get is practically 0. Which is
Is that
unusual.
6?
Mhm.
Oh, I can easy math.
So what does that mean? What that means is that they picked the point of attachment for the T right here pretty much perfectly, pretty close to the center of mass, so that there is basically these two guys cancel each other out, and there's very little extra force that Fy needs to exert in order to keep the whole thing balanced. Do you see what I'm talking about? So it's not usually the case that the Fy is going to be 0 here, but it has to do with the particular point of attachment that they chose for this sign. Fx, now Fx is not going to be 0, but we're not going to be able to do that with torques, because no matter what point I pick, Fx is still pushing into that point, right? So,
Oh, if you picked it outside of this thing.
right, I can pick it out here, but then you're like,
Could you pick it up the other end of the D? No.
What's that?
because-
yeah. So instead, I'm going to do sum of forces to find Fx. And it's going to be fairly easy because when I take a look here, almost all of my forces are vertical. And the only one that I have to consider is the horizontal component of T. So if I do the sum of forces in the x direction, then I get Fx pushing to the right, and I get T times the cosine of 35 degrees pulling to the left. Here's my Fx on my beam. All of the other forces are vertical. Here's my tension T. I scratch it out and replace it with its components. T sine 35 pushing upwards, and T cosine 35 pushing to the left.
And the reason it's cosine is because
It is adjacent to the 35-degree angle. And cosine is adjacent of right angles.
so then
And all
oh,
of that.
sine
all
will
that
sine
is
also
there.
be
Sine is opposite to the 35-degree angle. You want to think of a vector as being formed by its two components, the x and the y components, right? If this is my angle, this component is opposite to the angle. This component is adjacent to it. It makes up the other leg.
that
It makes up the other side of the angle.
it's confusing when it's put on the other end.
Mhm. Right, just visualize it being choop, like that. It's easier to find the adjacent one than the opposite one. And so since we already know the value for T, is 708 newtons, we get Fx is equal to T cosine 35. And that is equal to 580 newtons. Just like that. So you can see that the pivot is basically just pushing horizontally. And it's doing that to resist the force of the cable pulling that beam back into the wall. Does that make sense?
So you had to choose the point for the first one because no force.
Yep. Exactly. Cool. I'd like to look at one other that was a homework problem. I think it was number 13. Yes. So number 13, we have a table, and our table has a length of 2.2 meters. Which is going to be in the neighborhood of like 8 feet. And it has 2 legs, and the 2 legs are centered. They are 1.2 meters apart. And the table is 0.8 meters high. So because the legs are centered, then by a little bit of subtraction and division, you can figure out that that leg is 0.5 meters from the end. And now what happens is that somebody comes along, and we're not going to say who, but their mass is 66 kilograms, if you know what I mean. And they're going to sit right here near the edge of the table. And so the question is, what is the closest that this person can sit to the edge of the table without causing it to tip over? Here's your problem. Okay. So how are we going to approach this?
Pre-thought diagram.
Good. Exactly right.
If you didn't say that, we'll slap you.
It took a lot less time this time. So we need to have some things. Well, first of all, we need to know the weight of the table, because if the table has no weight, then the answer is it can't sit anywhere near the edge. Turns out it's a 20 kilogram table, so we're going to call that weight 200 newtons. And of course, it pulls down through the center of mass. Meanwhile, we have a 660 newton force there. Now, there are 2 forces that we have neglected so far. And those are the normal forces here and here. N1 and N2. The 2 legs are pushing. And at first you might think, well, they're going to push up equally, but that's not the case. And the reason that's not the case is this. When the 66 kilogram person is sitting exactly in the middle of the table, we agree by symmetry that N1 has to equal N2, right? But now as that person moves to the right, that's going to increase the value of N2, and it's going to decrease the value of N1. What remains constant is that N2 and N1 have to together add up to the total weight of the things that are resting on them, which is 860 newtons. This remains constant, but how they are distributed will depend upon where the person sits. Does that make sense? Now, this person is going to sit. He's going to sit as far over as he can. And so we are going to say that the sum of torques for that person, let's take the pivot point to be this leg of the table right here. Does that make sense? Because when he flops over, she, it could be, right? When he or she, or it, flops over, then it's going to be around this leg of the table. And so if we call this point of rotation point O, then the sum of torques about point O is going to be. Now, in the other class, there was great confusion about distances, because what our solvers in the other class wanted to do was they wanted to use this distance right here. This is a really bad idea. The reason it's a really bad idea is that, number one, I have to sit and figure out that distance using Pythagorean theorem. And number two, I have some unknown angle that I'm going to have to calculate also. And then I'm going to have to do distance times sine of the unknown angle that I had to figure out, and blah, blah, blah. Let's cut to the chase, shall we? When we do force times distance times the sine of the angle between, there. What we're doing is force times perpendicular distance. And you can see that the perpendicular distance between the table and the force, the perpendicular component of that is this guy right here. And I can read that straight off the diagram. It's 0.6 meters. Just like that. This is the key thing that this problem teaches us, is how to read perpendicular distances correctly. That force goes all the way down until it is perpendicular here, like so. And we can read that distance straight. Likewise, we're going to have an unknown distance x, and that unknown distance x is the same as this distance right here. So that when I do sum of torques about 0.0, what I get now is, starting at the left, N1 times 1.20 meters times the sine of 90 degrees, because N1 is perpendicular to this distance, times -1, because this is a clockwise rotation around 0.0. N1. Yeah, the torque exerted.
Oh, because it's on that camera.
Yeah, because
It's on the left.
Yep. Meanwhile, we get a counterclockwise torque of 200 newtons times 0.6 meters times the sine of 90 degrees. Well, it's already perpendicular distance, so we've taken care of it. Then finally, we have a clockwise torque of minus 660 newtons times an unknown distance x. And all of that has to equal 0. Now we feel pretty happy with ourselves, but we have two unknowns. We have the normal force in 1, and we have the unknown distance x. There's one thing that we haven't used yet. We have not yet used the fact that this fellow is the furthest over he can possibly be, right? The question was, how close can he sit without actually tipping? So to get that, I want to sort of make a fool of myself here and examine the tipping issues. I need a chair that is not broken to do this. Okay, so if I sit here, you can see that this is very similar to the situation we have in the problem, right? There are 4 legs in the chair, so technically there are 4 normal forces pushing up, right? And all those 4 normal forces have to add up to my weight. Well, assuming that I'm... But as soon as I do this, I begin to tip, right? And I have to work really hard not to tip. And when I tip, what becomes true about the normal force exerted by the back legs?
Does the front legs go on the ground?
Right. I'm talking about these, the ones behind
Oh,
me. It becomes 0. That's right. Right at the tipping point, this force, this N1, becomes 0. And that is the additional information we need to solve the problem. This term disappears. Poof. And because of that, I have an easy solve for x. Everybody solve for x. Go. and just estimating, I'd go with about 0.2 meters. Uh-huh.
I think you forgot it. We're all having trouble.
Is 120 over 6.
Yeah, 0.18 meters. Now, and so we go, hey, 0.18 meters, we're done. We look in the back of the book. Back of the book says 0.32. We go.
Teachers, pardon the interruption for afternoon announcements. In recognition of Black History Month, students may wear African attire on Friday, as with other dress-down days. Rules of modesty apply. Please see Mr. Firestone if you have a specific question about this clothing.
I'm so
Wait, this Friday we wear vector?
Hang on a
Kathy
second.
Worthington, report to Mrs. Keller. Thank you.
Okay, so the reason that we got that was that we didn't answer the question. The question was how far from the edge of the table. But notice where our x is. Our x is from this point of rotation right here.
So you have to subtract from.
So we need a little bit of subtraction, that's right. So we have 0.50 minus 0.18 is 0.32 meters from